What I want to do today is to give a counterexample to the Cantor Diagonalization argument. That is to say, to give an example that shows that the argument does not work for infinite sets. Note that I'm not saying that the reals don't have a larger cardinality than the natural numbers. I'm merely pointing out that you can't use Cantor Diagonalization to show that particular fact. So what I'm going to do is use base 2, and I'm going to use instead of decimal places, we'll use bit places, and then we have the bit point and the bit position. So let me go over real quick an example of the existing idea behind the Cantor argument. So what we have along the horizontal axis are the bit places numbered to n and continue on to infinity. And then down here is the list indexes. Now I'm going to start at 0 because it makes the functions better, easier to define. So here we end up with the bit points implicit over here. And then usually what you'll see is random numbers, set in here for all of the various places. Etc. This will go on to, these all go off here. And the idea behind the Cantor diagonalization is to take all of these along the diagonal and change them from their current value to the opposite value, and that's called D. And what that's supposed to do is then end up with a number that does not exist in this list, supposedly. So in this case, this one gets changed from a 0 to a 1. This one gets changed from a 1 to a 0. This one gets changed from 1 to a 0. This is 1 to 0. And suppose we had a 0 out here just to make it 1, and that continues on. So that's the normal argument that then says, well, since D is different from every single element in my list, then therefore this shows that the number of rationals is actually larger than the number of natural numbers. Of course, there's actually a problem with this, and what I want to do is show a counterexample. And the idea behind the counterexample is to use an LD U matrix, and we'll fill L with basically all ones, and D with all zeros, and U all zeros. And the plan is then to show that D as it's built, or even if you were to just infer its value, that it is already in L and always will be in L. So in order to do that, what we do is we're gonna go ahead and define a couple of functions. I'm going to define this function f, which stands for flip. And what I want to do is make it so that f of 0 is 0. And I want to make this so that that becomes f of 0 becomes 0.0. I want f of, say, 13, which is f of 1101 base 2 to be 0.1011. So you see what I've done is this has flipped here, this one has gone here, this one has gone here, this one has gone here. And so again, if we wanted like f of 7, then that's the same as f of 7 base 2, which is going to be 0.111. So how do we define that? Well, what we say is that for every ck, where that's an element of either 0 or 1, for every bit position, whenever we have ck times 2 to the k, then what we want to do is convert that to ck times 2 to the negative k plus 1. And that essentially does the flip for us. I also want to define a second function. We're going to call it g on all the non-negative integers. That gives us the number of ones in a row, so a given number of ones in a row. So we want g of n to be n ones in a row. And so, for instance, g of 0 is 0, g of 1 is 1, base 2, g of 2 equals 3, which is equal to 1 base 2, g of 8, for instance, is 255, and that's base 2. So you can see. And we define that by saying that g of n is 2 to the n minus 1. So we now have two functions defined that let us create a flip and also let us create a specific number of ones in a row. So the idea behind this is to essentially come up with our list and do f of g of 0. So here's our bit points along here to infinity, and these guys, and then we have f of g of 1, f of g of 2, and so forth and so on all the way out like that. So this is essentially the idea of what we are going to build as our list. So what we want to say then is that our list is equal to, let's see, their list L is equal to the set of all f of g of n for all n greater than or equal to 0, the non-negative integers. Okay. If we do that, then we take our idea, then what we've ended up with is something that looks like this. And we'll end up with all zeros across the top here. We'll end up with a 1, 1, 1, 1, 1, etc. Down here we'll have all 1s, and then 0, these are all zeros down here. And it ends up looking like this. So you can see we have our lower lower part here, a diagonal here, and our upper part here. So if we use angle brackets to denote the bit place, then if we say D at bit place M, then that's the mth bit place of D. So if we had a 4 here, then D4 means this bit place in whatever D happens to be. So, and that would end up being, you know, down in here. Now, if we take brackets, square brackets for the list index, then L5 is going to be the 6th element. And the reason is because we started at 0. Again, because it just makes the equations a little bit simpler. So if we were to say something like L5 angle bracket 4, that would mean list element 5 bit place 4. And the reason for this is just to make it easier to talk about things. So, so then how do we create this D, which is the diagonal? Well, the diagonal is to change any of these D sub m's to their opposite value. This value is 0, so we change it to 1. This value is 0, so we change that one to a 1 and a 1. And as you see, what we end up with, the diagonal elements creating D is always the same as one of the elements in the list as we create D. In fact, what you end up finding is that for any DM, so any bit position DM, that's actually the same as the list element M, bit position M. So then, well, what's the limit as we just continue this D along? Well, let's say D is equal to the sum of D sub I times 2 the negative I. And the negative I puts it in the right spot here. I equal 1 to infinity. And this then is equal to 0.1111 and all the way out. Also notice whenever we look at the limits, I equals 0 to infinity of L sub I. Well, what's that? That's the limit. I equals 0 to infinity of f of g of I. And that is also the same number. So you can see what happens is D actually happens to be the limit of the list, and so D is going to be in the list itself. Now you may say something like, well, wait a minute. I have, just by inspection, I can tell you that D is going to be an infinite number of ones just by looking at it, right? Which isn't how it was defined in the original Cantor Diagonalization, but that's perfectly good. Well, then I'm going to come up with a number P, which is an infinite number, the same infinity number of decimal positions set to 1. Okay, then what do we notice? Well, we notice that f of P is D. And so, again, at this point, we realize that D is also still in our list. And if you want to invoke G as well, what you can do is just say there's a number Q that's representative of the infinite number of ones in D. then G of Q is going to be a bit position. Oh, this is actually P. And then F of G of Q, which is equal to F of P, is equal to D, which is in our list. This is a list element in the limit. So as you see, that's essentially a counterexample showing that you can't use this in order to show that for countably infinite lists. For finite lists, of course, it's obvious that yes, you'll come up with a D value that's not in your particular list. Now, normally, when people use this argument, they're using some kind of list where it has randomly set to zeros and ones. And the problem there is that essentially you're saying that the list itself is static in the sense that it doesn't change but doesn't have a limit. But then that essentially is not an infinite list. So it stops growing in size. In other words, that the list doesn't go. Now, the static list basically is the problem here. So you end up with something where you're saying the infinity of the list going in this particular direction is somehow more than or less than the infinity of D going in this direction from the list contents. And that, of course, doesn't work. Anyway, I hope that kind of gave you a flavor for a counterexample. There's probably a whole bunch more counterexamples based off this same idea to show that it's not going to work for an infinite number of lists, i.e. a number of lists that are infinite in size. Anyway, thanks so much.